Hi all. Last day we have discussed this lemma. In this lemma, we can see that sufficient condition for getting this d as a alternating function. The statement is d be a two linear function with property that uh, d of a equal to 0 for any a with any 2 by 2 matrix A with equal rows. Okay, so then you can easily get d is alternating. So that means this is sufficient to get d of a equal to 0 for matrix with equal rows. Then that will imply that d is alternating. So in this lemma, today we discuss this lemma. This lemma deals the general case for this, or this is a sufficient condition for an n-linear function is to be alternating. So we start with a n linear function here of n by n matrices over k. Suppose D has the property that D of a equal to 0 whenever two adjacent rows are equal. Okay, it is enough to get this. It is enough to check that D of a equal to 0 for any matrix with adjacent equal adjacent rows. So then that D will satisfy the conditions for alternating function. The definition of alternating function is, the first one is d of a should be 0 for all a with two equal rows, and the second condition is d of a prime should be equal to minus of d of a, where a prime is obtained by interchanging any two rows. So this is the definition of alternating n linear function. So in order to get this d is alternating, we just assume that d of a equal to 0 whenever two adjacent rows are equal. Okay, so we need to prove that the statement, I'll write the statement A. The statement is d of a equal to 0 for all a with two equal adjacent rows. So we need to prove that A implies 1 and 2. Okay, so this is the lemma. So we will prove that whenever two rows of A are interchanged, then we can get a new matrix A prime. Then D of A prime can be written as minus dA. And before that, we consider if A has this, A prime is a matrix is obtained by interchanging two equal rows, adjacent rows, adjacent rows, not equal, two adjacent rows. Okay, adjacent rows. Suppose we have a matrix A prime. A prime is obtained by interchanging two adjacent rows, say ith and I plus 1 row. Suppose we have a matrix like this, we will prove that this d of a d of a prime is equal to minus d of a. That means whenever we interchange two adjacent rows, we can get a negative sign out from from d of a. Okay, so this can be proved using the previous lemma. You consider the matrix A as alpha 1, alpha 2, etc. alpha I plus 1, etc. alpha n. Suppose this is our A, and A prime is nothing but alpha 1, alpha 2, etc. alpha I plus 1. So this is in the place of ith row, and alpha I, this is in the place of I plus 1th row, etc. alpha n. Okay, so we need to prove that d of a prime is equal to minus d of a. Okay, first we will prove this result, then consequently we can get the second result. Okay, the interchanging of arbitrary two arbitrary rows. Okay, before that we prove this one. To prove this, we can see that d of uh, the matrix alpha 1 with the rows alpha 1, alpha 2, etc. Alpha I plus alpha I plus 1, comma alpha I plus alpha I plus 1. So these two rows, I'll put ith row as the sum of these two rows, and similarly I plus 1 row as sum of these two rows, and so on, etc. alpha n. So this is alpha I plus 2. In the I plus 2 position we have the same row of this A, and all the way up to alpha n. Now this matrix has two equal adjacent rows. Okay, by our assumption A, d of a equal to 0 for all a with two equal adjacent rows. So therefore this value, this d value is 0 by our assumption. That means we can see that this since this is d is n-linear, you can split this, or you can use the linearity first in the ith position, then in the I plus 1th position. So the first term will be d of alpha 1, alpha 2, etc. alpha I, this is in the ith position, comma alpha I plus 1, alpha I plus alpha I plus 1, alpha I plus alpha I plus 1. So this is in the I plus 1th position, and alpha n. The second term will be d of alpha 1, alpha 2, etc. Alpha I plus 1. This is in the ith position. The I plus 1th position we have the sum of these two rows, etc. alpha n. Now you can write this is, again you can split, or you can use the linearity of this I plus 1th position. Then this can be written as d of alpha 1, etc. alpha I. In this position we have alpha I itself, etc. alpha n, plus d of alpha 1, alpha 2, etc. alpha I plus 1. This is in the ith position. Sorry, this is alpha I. In the ith position we have alpha itself, and in the I plus 1th position we have alpha I plus 1, etc. alpha n. Okay, so this is the second term corresponding to the splitting of the first term. From the second term we can get again two terms. The first term corresponding to this term is d of alpha 1, alpha 2, etc. In the ith position we have alpha I plus 1. In the I plus 1th position we have alpha I, etc. alpha n, plus the last term will be alpha 1, etc. In the ith position we have alpha I plus 1. In the I plus 1th position we also have this alpha of I plus 1, etc. alpha n. By using a is nothing but d of a equal to 0 for if a has two equal adjacent rows. Therefore this value is 0 because this matrix has two equal adjacent rows, alpha I here, and this can be written as alpha 1, alpha 2, etc. alpha I, comma alpha I plus 1, etc. alpha n. So this is nothing but our a. And what about the second term? The second term is d of alpha 1, alpha 2, etc. alpha I plus 1. So this is in the ith position, and alpha I, etc. alpha n. And this is nothing but our a prime. A prime is obtained by interchanging ith row and I plus 1th row. So this is our d of a prime, and this will be 0 because this has I plus 1 alpha I plus 1 in the ith and I plus 1th row. So we can get this value, this sum is 0. Then you can write this as d of, this is our a plus, and this is d of our a prime. So this implies d of a prime is equal to minus d of a. So please note this, when you interchange adjacent rows of a, you can get d of that new matrix is same as minus of d of a. Okay, next we will prove when we interchange the ith and jth row of a and this b is obtained by, this is obtained by interchanging ith and jth rows of A. Okay, so we will prove that this d of b is also minus of d of A. This is our next claim. First you write this b, or first we write A. A has rows alpha 1, alpha 2, etc. alpha I. We have alpha in the ith position, etc. alpha j, etc. alpha n. Okay. So what is B? B is obtained from this A by interchanging ith and jth rows of A. So that is alpha 1, alpha 2, etc. alpha j in the ith position, etc. alpha I in the jth position, etc. alpha n. We have to establish this identity d of b is equal to minus d of a. So we have already proved that whenever we interchange two adjacent rows, then we can take a minus sign out. Okay, so we will prove that this b can be obtained from a by successive interchanging of equal adjacent rows, not equal adjacent rows. That means, for example, if we have 10 rows, alpha 1, alpha 2, etc. alpha, this is suppose alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, alpha 8, alpha 9, and alpha 10. Suppose you have this much rows, then how will you interchange this alpha 3 this alpha 3 and alpha 8? Okay, in order to interchange these two rows, we first interchange alpha 3 and alpha 4, then interchange alpha 4 in the position of alpha 4 we have alpha 3, then again interchange these two adjacent rows, then interchange these two adjacent rows, then interchange this, and then interchange this. So we can see alpha 3 in the position of alpha 8. So this is the 8th position. So when you interchange this much consecutive by interchanging these successive interchanging of adjacent rows, so we have total this much interchanges, 1 2 3 4 5. This is nothing but 8 minus 3 interchanges. So we have 8 minus 3 interchanges is required to get this alpha 3 in the position of the 8th position, or in the position of alpha 8. Now when you interchange this much successive interchanging of adjacent rows, you can get the present positions are alpha 2, alpha 4, alpha 5, alpha 6, alpha 7, alpha 8, alpha 3, alpha 9, alpha 10. So this is the present position of rows of A when we interchange when we apply 8 minus 3 interchanges. Okay, now we need to bring this alpha 8 in the position of alpha 3. So we need to bring alpha 8 here. That requires 1 2 3 4. This requires only 4. Okay, because we have if you have one interchange, then alpha 8 can be seen in this position of this, and if you interchange again, then alpha 8 can be in this position, and then this and this. Okay, so this total interchange is one. This much interchanges are needed. That is actually 8 minus 3 minus 1. Okay, it doesn't require 8 minus 3 interchanges, because the position of 8 is alpha 8 is in the 7th position, so it requires only this can be written as now alpha 8 in the 8 minus 1th position, so it requires again minus 3 interchanges to bring this alpha 8 to the position of alpha 3. So when you consider the generalization of this, so we have this alpha 1 etc alpha I etc alpha j etc alpha n. To bring this alpha 1 bring this alpha 8 in the position of alpha j, we have alpha I minus 1 here, alpha I plus 1, and we have brought this alpha in the position of alpha j etc alpha n. This requires j minus I successive interchanges of adjacent rows. So this much I put it as k. Then this k interchanges of successive interchanges of adjacent rows are required to bring this alpha in this position. Now we have to bring this alpha j in this position. It requires if we have alpha 1 etc alpha I minus 1 alpha j alpha I plus 1 etc alpha I etc alpha n. This requires j minus 1 minus I interchanges. So this is in fact j minus I minus 1, that is k minus 1 interchanges successive interchanges of adjacent rows. Okay, so ultimately we can interchange this alpha and alpha I and alpha j using the successive k plus k minus 1 interchanges of adjacent rows. Okay, so from each interchange of adjacent row will bring a minus sign out. Okay, so this d of b can be written as minus 1 raised to in each successive interchange of adjacent rows make this minus 1 or that bring this minus 1 out, then we can get total j minus 1 plus j minus 1 minus 1 successive interchanges. In each successive interchanges of adjacent rows bring this minus 1 side minus 1 out, then that will be d of b will be equal to this raised to this number minus 1 raised to this number into d of a. Then if you put this j minus I as k, then this will be k plus k minus 1, that is minus 1 raised to 2k minus 1 times d of a. So that is equal to minus d of a, because this is always an odd number. So this is d of b is equal to minus d of a. So this shows that whenever we interchange any two arbitrary rows of a matrix, then d of b is equal to d of minus d of a. So interchanging of any two rows will cause a minus sign out. Okay, so this is the key idea to prove the two statements. We need to prove that this d is alternating. So first of all we have we can prove the first result. The first result states that d of a equal to 0 whenever a has two equal rows. So suppose we have a equal to alpha 1 etc alpha I etc alpha j etc alpha n. Suppose alpha I is equal to alpha j. Our assumption is this a has two equal rows, say ith and jth row. Okay, if this ith and jth rows are equal, and if it is adjacent, then we are done. Otherwise you can get this this can be suppose this can be this d of alpha 1 etc alpha I alpha j etc alpha j minus 1 alpha j plus 1 etc alpha n. Okay, so this requires, this is same as d minus d of a, because it requires this this matrix can be obtained by interchanging the successive rows of this adjacent rows of this A, then D of this can be written as minus d of a if the number of interchanges are odd. Otherwise this will same as plus d of a if the number of interchanges of adjacent rows are even. So anyway, this value is always 0 because alpha, our assumption is alpha I and alpha j are two equal rows. Okay, two equal rows of a. Then if this by a we can say that this, since this matrix has two equal adjacent rows, then d value is 0. That means this implies d of a is also 0. So this proves whenever a has two equal rows, then d of a is equal to 0. Now for the second, we can easily write the interchanging of any two row will cause a negative sign out. So that we have already discussed in this case. If b is obtained by interchanging any two rows of a, then d of b is same as minus d of a. Okay, so this is our d of b. D of b is equal to minus 1 raised to 2k minus 1. This implies, sorry, this is in fact d of a. This times d of a, that is equal to minus 1. So this implies d of b is equal to minus d of a. This b is obtained by interchanging two rows of this a. So this proves the lemma, and using this we will establish the existence of n-linear functions in n and f. In m and k, where k is the commutative ring with unity. So in the next class we will discuss the existence of n-linear functions, n-linear alternating functions, as well as the n-linear determinant functions.